we now want to define the integral of a function on a C1 smooth curve. So the setting is gamma from AB to Rn is a C1 smooth curve, and we are given a function f from image of gamma to R, which is continuous. F from image of gamma to R continuous, and we want to define what the integral of f on gamma is. So before we make the definition, I can directly give the definition and say that this is by definition the definition of the integral, but that would not make much sense because mathematical concepts are never defined without some thought put into that. So what is it that we are trying to capture by the integral? When we defined the Riemann integral, we had a specific goal in mind. We had to somehow get the area under the curve. So there was a specific motivation as to why we proceeded in the way we proceeded when we defined the Riemann integral. So let's translate this to a physical situation. What you do is imagine this wire, imagine this image or the trace of gamma to be some sort of wire lying in space. Wire as in a physical actual wire made of some metal or something. And say you want to find out what the mass of this wire is. Well, what is the natural thing to do? Well, locally the wire might have different densities at different points. So if F is the density, or rather if F of gamma of t is the density of F at gamma of t, then you would think that this curve has net mass, or this wire has net mass summation over I f of gamma of ti norm gamma of ti minus gamma of ti minus 1, where ti, where t naught dot tm is a partition. Just a moment, a partition. This is a natural approximation to the net mass of the wire. What we are essentially doing is we are taking small segment of the wire, and you are looking at the length of that wire, and then we are multiplying it by the density. Here the density would be mass per unit length of the wire, not mass per unit volume, because a wire is a one-dimensional object. It has no volume per se. So this is a natural way to approximate the mass of the wire, and as expected, as you make this partition finer and finer, you would expect that this sum that we see here in fact converges to the actual mass of the wire. Okay, so it is also easy to see that this sum, as you make this partition smaller and smaller, it actually converges to the integral. So I ask you to make this precise in the exercises. So let me just state what I want to do as a definition now. Definition if gamma from AB to Rn is a C1 smooth curve, I'm going to restrict this definition to a C1 smooth curve. It can be done for rectifiable curves also, but I will not do that at this point. So let gamma from AB to Rn be is a C1 smooth curve, and f from image gamma to R is a continuous function. Then integral over gamma of f is by definition integral of AB f of gamma of t norm gamma prime of t dt. This is by definition, and in the exercises you will show that the sum that we wrote down, this approximate sum, sort of converges to this. What does converge mean will be made precise in that exercise. Okay, so this is a natural definition of the integral of a function along a curve. Now, let's uh, try to analyze this definition from a different physical perspective. One of the wonders of mathematics is the same object, in this case the integral of gamma, can be interpreted in different physical terms depending on the situation. So a single mathematical object could model several real world objects. A set of 3 could model set of 3 chickens or a set of 3 eggs. So in some sense, mathematical definitions and concepts are abstractions of real world concepts and definitions, and therefore there is a scope that a single mathematical definition could capture several real world definitions, and that's what is going to happen here now. So what you do is go back to the old interpretation, as that is, view gamma as the trajectory of a particle. Under this physical interpretation, we know that non-gamma prime of t is nothing but the speed. It's nothing but the speed of the curve. Okay. Now, you can think of non-gamma prime of t dt as the arc length element, some sort of infinitesimal arc length element, or infinitesimal arc length. This is not mathematically precise, but of course we are now wearing our physicist hats, and when we are wearing physicist hats we get the rights to be a little bit imprecise and vague. At the cost of rigor comes intuition. Okay. Now, since this non-gamma prime of t dt is some sort of infinitesimal arc length, we can introduce this pseudo notation ds for this quantity non-gamma prime of t dt. You would have noticed in several elementary multivariable calculus books that the arc length integral that we just defined would be denoted like this: integral over gamma f ds. And this is by definition integral a to b, the same thing, f of gamma of t norm gamma prime of t dt. Okay. So what we have called integral over gamma of f is sometimes denoted by integral over gamma f ds for this physical reason that you can interpret this quantity non-gamma prime of t dt as some infinitesimal arc length. Now, one of these goals in the next few videos is to make the expression, what is the meaning of this expression equal to ds, to make that precise. ds actually turns out to be a differential form on it, the arc length form on the curve, and integrating the arc length form actually gives you the arc length. So one of the goals, or rather one of the nice byproducts of the theory we are going to develop, is we can give a meaning to the physicists' use of this notation ds. So for the time being, this is just a notation. The physical interpretation in terms of infinitesimal arc length is just a vague intuition. It's not precise. We will make it precise. Okay. So this is the rudimentary stuff about integral on curves. Now our goal is to define the integral of a vector field on a curve. So a vector field is nothing but a set of arrows, one arrow for each point on an open set in Rn. So the common picture of a vector field is this, which you would have no doubt seen in basic treatments of multivariable calculus and vector analysis. So vector fields were introduced by the physicist Michael Faraday, and really you cannot do any sort of modern physics without this notion of vector fields. The most common vector fields you would have definitely come across in earlier studies is the electric field, the magnetic field, the gravitational field. So essentially the notion of a vector field sort of gives a geometric picture that replaces action at a distance with a more dynamic picture. So these vector fields also arise in things like hydrodynamics, where these vectors could represent the velocity of a particle at this point or something like that. So again, the same notion of vector field, a single mathematical abstraction, can be viewed as different things in different physical situations. Single mathematical object can be interpreted to mean different physical things. Okay, so for Faraday, he mainly considered force fields. So these were supposed to be the force that a unit mass or a unit charge is going to experience at this point due to some electric field or magnetic field or something. Okay, so let's make this definition precise. The definition is rather straightforward. Here is one situation where the mathematical definition does not complicate the things. Let U subset of Rn be an open set. A continuous function f, capital F, from U to Rn is called a vector field. If capital F is CK smooth, then we say the vector field is CK smooth. A rather tautological definition, vector field is CK smooth. Okay. In mathematics, one of the most common vector fields, indeed even in physics, is the gradient of a function, right? So this is going to be our example. The gradient of a function gives a natural vector field. So if f from U to R, let's put it small f, if f from U to R is C1 smooth, then the gradient f gives us a vector field. On U. The gradient vector field. This is of course just a continuous vector field. If the function f was ck smooth, then the gradient field will be ck minus 1 smooth. Okay. Now we want to define the meaning of integrating a vector field on a curve. What does this even mean? Again, it's best to get our physicist hats and put them on and think like physicists. So as I said, Faraday introduced this notion of vector fields to visualize force fields. So when you impart a force on a particle, the particle accelerates and it moves. So one of the definitions in physics that you have no doubt seen is if a particle moves a length L in a straight line, and the force is constant on this straight line, then the work done by the force is nothing but, so if I call this force capital F, it's nothing but FL. Okay, so if you have a force field and you put a particle and this force acts on that particle and it moves in a straight line, and this force field is happens to be constant along the straight line, then the work done W is just FL. So this is from basic physics. Now the question is, in general, a force field is not going to be constant. It's going to typically vary by the inverse square law. Wherever the source is far away from it, it's going to become really small, and it's not going to be the same in straight lines. It's going to keep changing. Moreover, the particle need not move in a straight line when imparted by a force. Planets move around in ellipses around the sun, not in straight lines. Thank God for that. What is the work done in this more complicated scenario? Well, of course, we must reduce to the case that we are familiar with. So what you do is, suppose you have a force field and this particle moves in this really complicated way. Well, what you do is you focus and zoom in around a particular point. And as we all know, if you have a C1 smooth curve, if you zoom in enough, it's almost going to be a straight line. And the tangent is going to capture this straight line in a very good approximate way. It's going to be a good approximation. Now the force might be acting in some other direction, but the particle is moving here in this direction. So what you want to do is you want to take the component of this force on the direction of motion to compute the work done, and that is obtained by taking the standard inner product or the dot product. So if you partition AB, then we have a similar expression. Work done is approximately summation f dot, note this is now a function. So this is f of gamma of t. So let me erase that and write that properly. F of gamma of t dot product gamma of t, this should be ti, f of gamma of ti minus gamma of ti minus 1. Okay, approximately this is going to be the force approximately. So the reason why we had to take the inner product is to get the direction correct, so that we take the component of the force in the direction of motion. Okay, so of course, shrinking this partition, making the mesh of this partition finer and finer, we get that work done is equal to integral a to b f of gamma of t dot gamma prime of t dt. So this is the physical intuition behind the definition. So we can formalize this into a definition. If f from u to Rn is a continuous vector field or just a vector field, we have taken all vector fields to be continuous, is a vector field, and gamma from AB to U C1 smooth, then the integral of gamma along gamma of this vector field f is by definition integral a to b f of gamma of t dot gamma prime of t dt. Okay, so this is the rigorous definition of what the integral of a vector field along a curve is. So these are called either line integrals or I momentarily I'm not able to recall what the other names are, but the common name given for this is line integral. This line integral of a vector field along a curve. If in addition, if gamma were regular, that means gamma prime of t is never 0, we can define the unit tangent vector t of at the point gamma of t to be just by definition gamma prime of t by non-gamma prime of t. Okay, so let me just make a change. This is actually going to be a function of t. The reason is that I cannot treat it as a function on the curve because the curve could circle back and come back to the same point at a later point in time. So the tangent vectors are not unique at the curve. At different points, at different times it could revisit the same point at different speeds. That can happen, different velocities in fact. So this unit tangent vector gives you the direction of velocity at time t. Okay. Now the integral becomes integral a to b f of gamma of t dot product t of gamma of t ds. Okay, remember ds was our notation for non gamma prime of t dt. It was just a symbolic notation, and this really we have not yet made it precise what ds really means in terms of differential form. That is to come in the next video. Okay. Let's introduce some more notations that are familiar from multivariable calculus. This will motivate much of what is going to come in the theory of differential one forms. Essentially what we are going to do is make such pseudo notations mathematically precise. Okay. Now imagine the same situation. Write this gamma of t as gamma 1 of t e1 plus gamma n of t en. So essentially what I am doing is I am writing the components of the curve. So gamma is essentially gamma 1 to gamma n. Similarly, write the vector field f as f1 to fn. So gamma 1 to gamma n will be C1 smooth, f1 to fn will be continuous functions. Okay. Now when you expand out the definition of work done, you will get integral a to b f1 of gamma of t gamma 1 prime of t plus fn of gamma of t gamma n prime of t. This is just expanding out the dot product dt. Okay. Now we introduce yet another pseudo notation. We can denote this as, by definition, this is also integral over gamma f1 dx1 plus fn dxn. Yet another pseudo notation. This thing is yet another pseudo notation. Okay. So what is happening is we are introducing these notations which you have no doubt seen in an elementary course on vector analysis or multivariable calculus in anticipation of the theory of differential forms which is going to come. Okay. So the goal in the next few videos is to make these notations precise, and the key is to interpret this dx1 dx2 dxn as dual vectors to the standard basis. So more on that in the next video. This is a course on real analysis, and you have just watched the video on integrals on curves.